Good morning, everybody. I'm back. Finally, I had about a 2 week unscheduled break. So I had to go give a talk, and then I got unknowingly got committed. Well, I got committed to another talk that I didn't have scheduled. Um, so we'll get into all my stuff, what I've been doing on Monday morning. I don't really want to take time from our guest today. We got a lot to go over. We've been going over iron for how many weeks? I don't know, several weeks. And I've been mentioning that if you've heard any of the previous podcasts or YouTube episodes, I've been talking about how unbelievably complex it is, iron in the soil. I'm not particularly convinced that anybody's really, not that, really anybody really knows what's going on in the soil with iron. It's very, very complicated. And one of the strangest things sometimes has happened. And 10 or 15 years ago, they started finding some stuff in putting greens and so forth. And we're going to talk about iron dynamics in putting greens today with the author of today's paper, Dr. Obear. How are you, Doctor?
Great. Thank you for having me on.
Glen is... I think you're the first author that's published anything on like iron cementing layers in putting greens. Is that the case? I don't know of anything before this paper. Do you?
There have been, the only thing I knew about before this was a magazine article that was written in German.
Oh.
And that was the only thing I could find related to turf and iron cemented layers.
Oh, wow. Wow.
This is the first peer-reviewed paper that I know of. Yeah.
Well, Glen, I don't recall, I could be wrong, but I don't know if I've ever actually met you. Maybe at a meeting or so. I don't recall exactly. But why don't you tell me a little bit about yourself, what you're doing, what your background is, and how you got into turfgrass and so forth.
Great. Yeah. So I started out, in the turf industry by working on a golf course. And I grew up in Sheboygan, Wisconsin, and worked on the maintenance crew at Whistling Straits, and decided I wanted to get into that career field. And so my second year, and I was in undergrad, starting out, and I got an internship at a golf course in Hawaii called Kukio. And the course was about 5 years old. And during my internship there, the superintendent introduced me to a problem that we're talking about today, right? Where they had some layering issues in the putting greens. And, he had a lot of experience looking at these over his career. And there hadn't been a lot of research on how these layers form, or all these questions about what contributes to, how they form and how to deal with them. And so from that point forward, it was a turning point for me of wanting to get into the research side of what we do.
Okay.
And so after I finished my undergrad, I continued on with a master's degree at UW-Madison. I worked with Dr. Doug Soldat, and I looked at this issue and also studied bicarbonate, dynamics and accumulation in putting greens. And then I studied entomology at UW-Madison as well. And then after that, I went to Nebraska and started a PhD program to continue to look at the iron accumulation issues. A part of the way through my PhD program, I moved back to Wisconsin, and I started at X-Acto, which is a company that's who I work with now. So X-Acto makes wetting agents and adjuvants for the turf industry as well as agriculture. So my role there is I'm the R&D director, so I oversee formulation development, lab and field testing, and then regulatory as well. And so, so we make a lot of products that help make inputs more efficient, whether it's pest control or fertilizer or irrigation. That's kind of our focus, is making what you guys use more efficient. And so,
what was the old BASF line? It was at BASF, we don't make the products you buy, we make the products you buy better, or something like that. What was the old commercial? Something like that. It kind of reminds me of that. Yeah.
Yeah, it's similar, right? So, go ahead.
It sounded like, if I heard you right, that you may or may not have been thinking about graduate school, but when you went to your internship in Hawaii, and this the superintendent introduced you to this issue, that maybe spurred some critical thinking and some interest in pursuing that further. And is that what led you into to going into graduate school? That's what encouraged you, or were you thinking about it before
Yeah,
then?
I'd like to give the superintendent full credit. His name was Scott Nair, and he said, "Why don't you go to graduate school and figure this thing out?" And
Oh,
so
well, good.
I did go to graduate school. I don't think I figured it out.
No, well, yeah. I don't know if any of us figured anything out in graduate school other than how to mess things up sometimes.
True. Well, that's true. Yeah, yeah. How to put too much on your plate.
Yeah. Time
Yep.
management, maybe. I don't know
Yeah.
how to stay motivated and get across the finish line. I think that's probably what I learned in grad school. But
I can't. When you start out, you think that you're gonna do all these things, and then
yeah.
I mean, man, that was 2014. That's when this paper came out.
Yeah.
Can we have a moment of silence for the past 10 years? It's been 10 years.
Man, I know it's oh God, it's like a blink of an eye. Do you have any children?
Yeah, I have
Yeah.
two kids.
That
eight and 10. 8 and 10.
Oh, 8 and 10. Okay, so it's basically the same as my children. And that is like, they say you can't time travel is not possible. You have kids, you'll time travel real quick. I mean, you turn around, it's been 10 years. Like what happened? You were just in preschool and now you're in 8th grade. What? Like how did that happen? So that seems like it speeds time up hugely when you have kids.
It does. Yeah.
That's good.
Absolutely.
So you went and did some work with Doug, and then you went to Nebraska and worked with Bill, I guess, huh? Is that who was?
I did.
He was developing or creating, or I guess maybe it was you, some sort of system there, a fabricated system with columns or something with iron at one point. Was that Bill doing that, or am I crazy?
Yeah, it was me.
It was you doing that. Okay.
Yeah, it was for my project. Yep.
And that was for your PhD, and then somewhere in between there, you moved back to Wisconsin and kept doing it remotely.
Exactly. Yep.
Oh, okay.
Yep. I think the fabricated system was really cool, and I think someone could do something really special with it. But I parked that one and I focused on what I could finish remotely.
Yeah. Well, let's get into the paper then. So the paper we're going to talk about today, everyone, is your 2014 paper. This was in Geoderma. I'm pretty sure Geoderma is behind a paywall. At least this article I think is. I don't remember, but
probably
this is one of the first articles we've discussed in Geoderma, and I know Doug's put a couple papers in Geoderma over the years. So it's a good journal. The title of it is called "Soils with Iron Cemented Layers on Golf Courses in the United States in Geoderma in 2014." So you already answered one of my questions, like how did you end up finding a course in Hawaii? That was probably the first course you found, apparently.
Yeah, I can answer that quickly. I mean, as a scrappy, college freshman, I went on Google and Googled top 10 golf courses in Hawaii, and I printed my resume and put it in manila envelopes. And I mean, that's what are the odds that would work? But I think it showed up there the very day that someone backed out of an internship, and so the guy called me. And
you never know how things. Imagine what would have happened with your career or your direction if that person didn't back out or whatever. You didn't go to Hawaii. You might not have ever even done graduate school. Who knows where your life would have went? It's crazy.
Studied manganese instead of iron. Who knows? No, I'm just kidding.
Well, so let's talk about first, the introduction and the materials and methods. What, just kind of walk us through how you already walked us through how you first found the course in Hawaii. In this paper, you have a map that shows various locations of these course or these putting greens around the United States. But just walk us through, like from the beginning, before you, I don't know if you was this with Doug or was it, I guess it was Doug, he's on the paper. So, so before you even went there and before this project ever even existed, obviously this was on your mind. I mean, you found this course in Hawaii, or you were introduced it from the superintendent. How did it come about? How was it developed? And walk me through the initial stages of the project.
Yeah. So, I mean, just let's, put yourself on the golf course. Imagine you're standing on the course and, what do you see first? You see the turf, the density, the health of a putting green. And on all these greens in the low spots, where, kind of like where you'd have lateral drainage and maybe an outflow drain pipe. Okay. Where there was lower turf density, the soils were wetter in those spots. And it's like, those areas that we classically associate with having black layer or anaerobic conditions, and what we then looked at or discovered was, we took a sod cutter and we cut out 2 or 3 rows of sod from those edges, those low spots from the edge of the green. Stripped the sod away and then dug down through that sand profile, and they were USGA spec putting greens with sand over gravel.
Okay.
And so you saw that really dark anaerobic, kind of like smells like sulfur soil at the surface.
Mm-hmm.
And then down at the interface of sand and gravel, we saw these cemented red plate-like, cemented layers, and they were, cemented by iron. And
okay, so explain that. I mean, I've never actually seen this in person. So, like, if you dug down in there, if someone in a severe case, like you have a photo in here that's at least, I think it's a pretty clear case, but if you dug down in there, first of all, you see a low area of your putting green, or that tends to be anaerobic, or tends to it's not doing well. They might initially think it's some sort of black layer of sulfur, and it may be that. But you went all the way down to the gravel layer, which is 12 inches or more down, and at that interface, is it hard metal? Is it just like aggregated, dense, material that has some percolation, or is it just completely like a sheet of steel? I mean, what does it look like?
Not a sheet of steel, but it's like if you grabbed a plate of this stuff, you could snap it, but it would audibly snap.
Oh, so okay.
It's kind of like a conglomerated, powdery. It's really powdery.
Okay.
Yeah, especially once it dries out. But certainly it's the density of that would be higher than, or like the pore space in that would be much less than what's in the sand above. And so it's
a sheet that you can actually pick up if you handled it well enough. You could actually pick it up. But oh, really? Okay. Wow.
Correct. Yeah.
That would be a problem.
Like as you're shoveling it, you're picking up big plates of it with a shovel. Yeah.
Wow. Wow. Okay. So go ahead and continue. Yeah. So you saw this, you dug down and you see this, and please continue about how the project developed from there.
Sure. Yeah. So no, so you called out that if you first see that thing at the surface, and your natural thought then is, okay, we need to aerify, we need to do all these things to attack this surface issue. But digging down, the superintendent knew to dig down deeper, and that was so insightful because that's really what showed us more of a full view of what was going on. And so anyway, we at that time we physically removed the layers with shovels on many of the greens that were struggling, and think that could have provided some temporary improvement in drainage. The question then is what conditions are present that's making these layers form on greens that are only 5-ish years old. I mean, that's pretty young for something like that to happen, right? And so then that's when Scott made the comment, you should go get a master's degree and study this. So I went back to UW, continue with my undergrad program, but was in the soil science department and showed this to a lot of the soil scientists there, right? And so Doug was my advisor, or I worked with him in the turf program. But then
I got a question though. So you're an undergraduate, and you did an internship, and then you came back with some photos of this and shared it with the faculty there. Yeah. See that I think that okay. Let me just make a comment here, if you don't mind. The value in that sort of communication, I think, sometimes is fading. I mean, I don't know if undergraduates quite sometimes grasp the value of something as simple as that. The communication. In other words, the faculty are really there to serve you. They're being paid by state tax dollars to service you as the student and taxpayers and so forth. And you go back to them and say, hey, I see this stuff. And then from that, you see this huge project develop, and we start addressing problems that they probably very likely would have been many, many years before they ever, were introduced to this particular phenomenon in putting greens. Just because an undergraduate came and brought it to their attention. I think that's great. Fantastic. Well done.
And I thank you. I think it speaks so much to, I think about the idea of innovation a lot, and is there anything truly original anymore? Yeah, there is. But so much of the innovation comes from, we have our world, like let's say it's, managing golf course turf and soils. Someone else in another world that's related, like pedology, soil formation, for example, in this case, I showed Alfred, who's one of the co-authors on this. He saw pictures of this, and he was like, "Oh, I've studied this extensively in alpine forest soils, and
Okay.
this looks exactly like a spodosol, and like he had a whole vocabulary, and
Yeah.
there's a name for it, and there's a whole system that's in place that quite literally applies to what we're doing, except there are some differences. So I think that cross pollination of reaching out not just to the people that are right within our inner circle, but branching out to, a broader network, in this case at a university, like a university provides that. And that's, I think, that's the value of that is I bet there were 4 other people in that department that one person would be focused on the biology aspect and someone else would be focused on the soil physics aspect. And everybody has such a useful insight to it.
There's physics and chemistry, and there's all sorts of stuff going on here in this particular project. Well, good. Thanks for the introduction. So that's kind of how it came about, and that's how it got on the table and started developing. I assume either Doug or Alfred had some funding, and you were able to get in and start the project and get it going.
Yeah, I can comment on that. Doug had a USGA grant to study bicarbonate, and then this really became kind of a side project or a tack on to that. And so this wasn't initially even in the program or for my my thesis, but it became a chapter of my thesis, and then it became my PhD project. So
perfect. Yeah. Well, let's get into it. That's the introduction, basically, and the material. And here's the for those watching. Here's the map of the locations. I don't necessarily know if we want to. We can go through the whole materials and methods if you want to, but just in general, sort of in layman's terms, walk us through the materials and methods, how you kind of scouted out these locations, how you diagnosed them, and then how you selected them, and so forth. You want to do that?
Yeah, I can do that. So again, I mentioned I initially started with a USGA funded bicarbonate focused project. And so the goal of that project, or one of the pieces of it, was to work with the USGA green section agronomists, and they would help find courses that would be interested in participating in the study. They would take these in situ undisturbed full profile samples in PVC pipes, and then send those to us at UW-Madison. And then we would, look at them and measure. The goal was to measure the bicarbonate or the carbonate concentration in the soil to see if any layers existed. And so then here we are with this big wealth of full profile soil samples. And I had just come from this internship where I saw this layering issue. And then lo and behold, in maybe a third of those samples that we got out of 30 something sites, about a third of them had some form of this reddish iron accumulation, cemented layer. And so the light bulb turned on, and it was, so it was quite, it was convenient to have one sample set that, applied to both studies. And so that's really what we did is we, this map shows all those sites that we took samples from, and then the ones that have the blue star, we went further in depth, and those are the samples that were analyzed for this paper.
Okay, perfect.
Yeah.
So for those people who are interested in table 1, these are the different locations that they studied. So it looks like you studied in Washington State, Wisconsin, New Jersey, Virginia, Florida, and Hawaii. So those are the 6 out of however many locations that you saw. How many would you identify? You identified 18. So out of those 18, you got 6 that you wanted to look at further. And let's now for now, here's what we're talking about. For those, now there's going to be a lot of people listening on podcast, Glenn. So we're going to be looking at photographs here, and this kind of really shows the point or the phenomenon that's occurring. But if we can use our best description ability for those people who might not be looking at the photo, what do we see here, Glenn?
Yeah, so this picture is showing what I alluded to with, in the upper left corner, it's showing a putting green that we actually were re-sprigging it. And so we had stripped away all the turf, and you're looking at the sand root zone or, soil profile, and then the gravel below. And we excavated out a huge, maybe, 20-foot wide by 30-foot long section of the sand. And that entire area that's been excavated out had that cemented layer.
Oh, really?
Covering the gravel. This entire green actually, every part that we investigated on this whole green had that layer underneath the sand.
Oh, really? Okay. Yeah,
yep.
I see.
That's what that's showing. Yep. Huh. And then, so that was 2008 in Hawaii, and then this is funny. I started doing this research, really just thinking that this was like this Hawaii problem, some kind of exotic thing that, you know, you'd have to go there to find. And then the picture on the upper right is literally from University Ridge Golf Course, which is I worked at for 2 years and and never saw this. And it was, you know, right in the backyard of UW's Turf Research Center where I worked for 3 years. And so the guy called me and he's like, you got to get over here. You got to check this out. And I just, I'll never forget that day. And, so that's, again, it wasn't everywhere on that golf course, but this was in one particular area where you see some reddish color at the top, above the gravel layer. And then this really darker black color below that red, which, you know, it could be iron, it could be manganese. So it's again, it's that cemented layer close up. You can see sticking all that sand together and really preventing a lot of that drainage from going through the sand down into the gravel.
Yeah, I say this with hesitation because I know the superintendent is probably not happy with this particular what happened there. You know, it is what it is. But from a soil chemistry perspective, this is awesome. Okay.
Yeah.
I mean, when you see this fading of this red right here and going, you know, it's going down, but you see this fading from this black layer where it's been completely turned into oxide, and you see this fading where there's probably some sesquioxides and some redox reactions occurring all in this red zone here, this little brownish red zone right above the black oxidized iron, or it could be aluminum or manganese. But that's to me, that's awesome. I'm sorry.
Yeah, it's fascinating.
It is really fascinating. I know the superintendents don't want to hear that. I'm sorry for them to have to deal with this, but it's really what amazes me the most sometimes is that, you know, the USGA spec greens are built for compaction. I mean, we need to maintain aeration. We need to maintain, you know, a turf grass growing in a location that gets a lot of traffic and, you know, and so forth. So it is what it is, and we have, you know, it serves its good purpose. But I'm surprised we didn't actually think of this 30 years ago when we were designing the USGA spec greens, because it is a perched water table. There is a very specific reason why it's designed that way with the particle sizes and the thickness and so forth for water movement and so forth. But when you hit that airified layer, well, we'll get to it. When you hit the gravel layer where there's just a lot of oxygen down there and the lower boundary chemistry of that upper layer of the 12 inches, there's a lot of stuff going on there. And I'm surprised we didn't really consider that at the onset of that. There's not much we can do about it probably, but it's fascinating to actually see this now. Anyway, I'm sorry. I'll be here for 4 hours talking about this stuff. Okay, so in C, what do we see? This looks more of like a fairway sort of thing, but it's not, right? It's still a green.
It is. This is a green. So it's this is in Wisconsin, the bottom two pictures. And so again, at another golf course where I never expected to find this issue, but I don't remember how we first came across it, but we got samples from them and we're able to look at a low area and a high, like a low poorly drained area where the lower right picture actually shows you have maybe some winter injury that has occurred. So it's, you know, suggesting maybe it's a spot where water accumulates and you might have ice forming and things like that, versus a well-drained slope. And this is one of the first spots where we looked at the difference between the iron concentration in the well-drained areas versus the poorly, or, you know, the depositional areas lower down in elevation. And so that's what that's showing. And in this case, we actually had an accumulation of iron at that 10 centimeter, like just below the, kind of at the bottom of the root zone, below that.
Yeah, like 5 inches down.
Rich.
Yeah, not very deep at all. Yeah,
not very deep at all. Yeah.
And what sort of concern or risk is involved when you're looking? This doesn't look near as acute as the letter, as the panel B does. But is it the case that even something such as this here, where we're talking, it's more of a faded, but obvious, but yet sort of faded accumulation potentially of iron or iron oxide? What sort of concern would that be for turfgrass health? Do we see something in those cases? I mean, is that what this is here? Is that what this is on this right panel?
I don't think that my personal opinion is I don't think that layer is causing that turf to die. I think that's a winter injury issue. But,
okay.
I mean, they're all connected at some point, right? With drainage and it's a 3-dimensional problem.
Yeah.
But I think I think the gray area is, I shouldn't use color because color is related to the problem here. I think where the tricky spot is, I think it's more obvious when it's like a dinner plate, hard cemented layer. But when you dig a hole in soil, you're gonna see red color.
Yeah,
I mean,
you're gonna see layers. You're gonna see layers. Yeah,
you are, and even if that layer, even if it wasn't iron, I mean, all putting greens have an area where there's more organic matter at the surface, and then a drop off where then there's no organic matter, and that surface is going to hold more moisture than the drier area below. And so I think this might just exacerbate that. That's my thought, is that it's almost like a mini version of the sand over gravel interface, where that one's really stark because the water just sits in that sand. It doesn't go into the gravel. I think over time that happens above as well, where you have a slightly finer textured, more moisture holding layer above a coarser textured sandy layer, and you've got more moisture being held there. It's wetter above and it's drier below. And so then you can see these. It's
possible, especially
again, layers can form.
It's definitely possible, especially if you're using potentially if you're using different sizes sand for your top dressings and things like that, where you're using ideally, I mean, the putting green is never static. I mean, it's always changing. So ideally you would be using the same particle size as when it was built, but it might have been built 20 years ago. I mean, who knows? So it's not possible to get the exact same thing, but what you're saying makes some sense especially if you do it enough to where you're forming, a textural discontinuity as like a salt, as a kind of a finite line or a layer there. Okay.
Exactly. Yep.
So you took some samples. Basically, I'll just sum up some of the materials methods. You took some samples and you analyzed those samples for various forms of iron. One thing that you mentioned many times throughout here, and I highlighted here, is the various types of iron analysis. You denote those as Fe sub 0 or Fe or O or Fe sub D and so forth. Yeah. Can you walk me through there and help explain what is the when you say the FeO to FeD ratios and all these other things, oxalate extractable iron and so forth? What are you saying there?
Yeah. So step back for a moment. So, what do we, when we take soil samples and send them to a lab, what are we usually looking at? Nutrient availability, right? And so they're running like a Malik 3 or some kind of some extraction that extracts a certain amount of the nutrients, and then we see, we analyze that. And so I've had a lot of people look at soil test reports and send in, like, they'll see this layer and then they'll be looking at like Malik 3 soil test results, and it doesn't exactly match up. It's not the right test for this. And so again, like, it's that's a whole other area of controversy. What is the right test for even for nutrient availability? But definitely those are not the right extractions to measure iron accumulation problems. This is not about plant available iron. This is
I would argue that Mega 3 is not a good test to measure plant uptake of iron. Well, no. I mean, for iron. Yeah, for iron, Mega 3 with iron is very poorly correlated. But go ahead. I'm sorry.
That's fair. Yeah. And so we have to go to a different toolbox of tests for this. And that's a challenge, right? Because all the major commercial labs easily offer the plant nutrient analysis, right? But or the plant available nutrients. So these are some more customized methods that are really designed to extract iron oxide. And so there's 3 different ones that we used. Total iron measures like literally all the iron in that soil, and that's, we never really look at total in like turf soil testing, but
I had a guy this last week. I was at the golf course show, and he was trying to convince. I was talking about soil tests, and he said no. No, you need to do total nutrient analysis. And I'm like, what? And he said no, total nutrient. You have a lot more there than you realize. And I was actually giving the talk, and I had to stop the show, and I was like, hold on, guys. Do not do total analysis. Okay, it's useless for turf grass management. Don't do. I had to tell him. I was like, don't do what he said. He was an audience. He's an audience member, and he was trying to contribute. But I was like, no. we're not doing. Yeah. We're not starting up another mythology or legend of doing total in. We should have been doing total iron the whole time. No. So what you're saying, Glenn, and I want to make sure the audience understands is that yes, you can do total analysis. He can do total iron. From our pragmatic, practitioner's perspective, it's not useful. From a scientific perspective, when we're trying to diagnose things and understand what's going on in the soil, it can be useful. And here's a perfect example of that. I'm sorry. Go ahead, Glenn.
No, exactly. Yep. Yeah, I think the only place I think it could be useful for looking at physical layering problems, drainage problems, things like that. But yeah, I agree that, I mean, what you're measuring is like the inside of a grain of sand that will never break down.
Exactly.
You're measuring that iron. So you're way overestimating, or not estimating. You're literally measuring everything there. That's not. I mean,
we're interested in knowing or having some confidence in knowing what is or will become available in the near future, and how that correlates to plant response. And total nutrients is I've never seen any evidence to indicate that total nutrients is in any way correlated with some sort of plant response. But like I said, in your case, when we're dealing with podology or mineralogy or something to do with the soil where we want to understand it further and maybe diagnose something, that can be useful. But from like a turf manager or superintendent's perspective, I had a room full of superintendents, and I think that's the first time they ever heard of total nutrient analysis. And the last thing we need is for all them to go, "Hey, I need some total nutrient analysis to know how much manganese." No. Let's stop that. So I'm sorry. I digress.
Yeah, and then you're starting over back to the early 1900s of soil testing from ground zero.
Yeah.
Because I know maybe like the current methods are not perfect, but we have a huge data set of at least calibrating like what Pace Turf's done with calibrating visual turf response to
we have some confidence in it.
There's a lot of information out there, and so starting over with a brand new method, it sounds like about 100 years of work. And so
so you speciated it. You did oxalate extractable iron and dithionate extractable. So what does this mean, oxalate extractable iron, in terms of what your purposes were for the study?
So in practical terms, those are the two different strengths of extraction. So oxalate is a weaker extraction, and dithionite is a stronger extraction. What's that?
Well, why is that important? Why was that important for your study to do that?
So what you can do is imagine you have on one extreme you have like really, really strongly cemented, old, it's been there for a long time. The dithionite, the FED, will measure that.
Okay.
And the oxalate will not measure that. It won't pick that up. And so you could, on the other hand, if you have iron that like was really fresh, recently formed, maybe in the last year or two, the oxalate will get all of that. And so you can actually do a ratio of the oxalate to dithionite, meaning like if you do the extraction and the oxalate gets all the iron, like those two extractions got you the same amount, that means that it was all fresh or more recently accumulated.
That helps me understand it. Perfect. Thank you.
Yeah, that's really the idea.
Okay. So if anybody's interested in soil, judging, they provide all the horizons and all this is probably Greek to most people, but personally, I love it. Because when you say spodosol, I know immediately what you're talking about in terms of like water movement and horizon formation, in terms of what's necessary to create that, what it looks like in general. Most people aren't going to know that. Most people aren't going to care about that. I get that. But personally, for scientific purposes, I love this stuff. You give all the Munsell color chart identifications of all the layers and so forth. So I know that was a lot of work, but thank you for doing that.
Yep.
Okay.
It's go ahead.
No, I was just saying. So we get into the results, and so let's just set the stage here before we go any further. So you've gone out, you have 6 locations around the United States, some in the continental United States, one in Hawaii. You did some core sampling. You took the core samples in. I think you actually split the core sample. You split it vertically, so you have 2 different core samples, and you're doing analysis of the iron in layers, I guess. So you're looking at the A layers and the various layers in the soil. And then you're speciating that iron to kind of get an idea of how old that iron is, or how freshly deposited it was, and so forth. as a means to kind of determine how are these forming, what are the factors, or what are the elements that are involved in the formation. You obviously have probably a pretty guy, especially with Alfred on here. That guy's unbelievable. I mean,
He is.
Oh my God. So he probably already knew, let's be honest. I mean, the guy's a genius, but you still got to go in, you got to do the work, got to figure out, make sure this is what it is. And yes, and sure enough. And so now we're here, we're looking at a scanning electron micrograph of one of the samples that kind of provides some of the evidence of what exactly is going on to aggregate these layers. You want to walk us through or explain what we're seeing in figure 3 here? The photograph.
Yeah, we made a thin section and sliced it very, very thin and put it under a scanning electron microscope, and you can actually look at the elements that are on that thin section. And so we were able to see that that iron is that medium gray color that's between grains of sand, kind of sticking those together and sitting against the gravel. So just another way to look at what our eyes already tell us or see.
Yeah. Well, it's, we're in science. We can't, we can have a hypothesis, but we can't just run with it. We have to actually have evidence to support it, or the evidence doesn't support it. And so you did this stuff. It's fantastic.
Yeah.
Yeah. Good. Well done. So as we go through the results, basically you find that there's some movements, there's some iron in the precipitate layer. There, in some cases, there was some aluminum in the precipitate layer, and there was some soluble organic carbon in some locations. Correct? Is that basically the gist of it? Now,
yep.
Let's see. There was one in here I wanted to. Let me look through here. Okay. So I wanted to read this one paragraph about pH because I did a couple videos on pH. I guess the last 2 I did on pH, and I guess people are interested in pH. So, So let me just read this, and then you can stop me or provide any comments. In all soil profiles, there was an accumulation of soluble organic carbon in the top 5 inches, or 4 inches, whatever it is. The soil profile from New Jersey, Washington, and Wisconsin, the low profile, also had higher soluble organic carbon levels in the iron cemented layer. Soil pH values were generally acidic, 6.1 to 7.2, in the profiles from Washington and New Jersey. But in the soils from Florida and Wisconsin, the low profile, the pH values were slightly higher and alkaline at the interface of the sand and the gravel. The soil profiles from Virginia and Hawaii, the low profile, had neutral or alkaline pH values in the top part of the soil profile, and the pH was acidic above the interface of the sand and gravel. And the reason I wanted to read that is because I want to make sure that we understand the setting. We're dealing with iron cemented layers at the interface. For those who may not be familiar, when putting greens are built, the USGA spec putting greens, there's a standard layer, or usually it's 12 inches thick, that is put on top of, most of the time it's a 4 to 6 inch thick layer of coarse gravel. And that layer, the finer textured sand above this coarse gravel, allows the water in the root zone of the soil, for the turf grass growing in the above layer. It allows water to be perched up there, but it also allows it to drain through. So you never really, well, except for in odd cases like this, you're not really ever going to be saturated theoretically. Theoretically, the water is going to go into the gravel layer and drain off. That's the way it should work in theory. I know that doesn't always work. But at the lower boundary layer of that 12 inches, though there's a 12-inch root zone, and then there's a gravel layer below that. At the lower boundary layer, when water is moving into the gravel layer, the area at the top of that 12 inches is going to be aerated. It's going to have air go into it much sooner than the lower boundary layer of that 12-inch root zone, right? And and you're not dealing. The reason I read that paragraph is because you're not dealing with all the same pH values. You're dealing with pHs that are acidic. You have some that are neutral, and you have some that are actually basic, above 7.0, right? So in our world, in the last couple of weeks, when we were talking about iron movement, I've talked about the reduction of iron. And generally speaking, the reduction of iron occurs greatest when there is less oxygen, when it's saturated. That's when water movement can occur. Iron reduction from Fe3 to Fe2 generally occurs more frequently in more acidic soils than in more basic soils. But you're dealing with all of them, and you found the layer in all of them. So that's what I found curious. I wanted to make sure that's clear to everybody, is that Well, I understand what Dr. Obear is saying, but my soils are basic. I'm not going to have much iron movement. Well, hold on, because he had one that was basic as well, alkaline as well, and he had a case where there was clearly an iron cemented layer formed in that case. So I just want to make sure that's clear. Did I miss anything on that, Glenn?
No, I think you just highlighted that. Yeah, pH is one factor, but the redox potential, or the how saturated and anaerobic a soil is, or the EH, the redox potential, is the other factor that we don't have an easy way of measuring. It's not, as soon as you dig the hole, that changes. So it's not easy to to get that value from a soil testing.
Yeah, especially when you're dealing with stuff like what you deal with when you're dealing with just at that little layer of 1 centimeter. And even like when plants are taken up, we're dealing with a very, very small slice of the rhizosphere where the redox potential can be quite different than what it is in the root zone. And we're taking a sample from the root zone and saying, oh, you shouldn't do that. Well, there's a lot more going on in there than that. And it has to do with the redox potential.
Absolutely.
And So you also mentioned here that the age of the golf course had little effect on any of the soil properties included in the analysis. I found that kind of interesting. I imagine, 30, 40-year-old greens might differ, but maybe not. In your case, you didn't find much variation from the golf course age in terms of the soil properties you looked at. That was
a small sample size.
That's true. I only had 6.
Yeah.
The pedogenesis. I don't know if I'm going to bore everybody with the pedology involved with this, but I do think some basic understanding of it would be nice. So in 4.1, you mentioned the iron cemented layers are found in putting greens that are regularly irrigated. Okay. And in some cases, this is what I'm sorry.
All putting greens. That's the pedologist saying, as if there are some that are not regularly irrigated.
Yeah. And this is what it said. I highlighted this right. In some cases, receive high levels of iron fertilizer. I'm going to come back to this in a little bit. Commonly as iron sulfate. To produce a dark colored turf grass, the downward movement of water, high levels of iron, and textural discontinuity are key factors in the formation of iron cemented layers. These layers form in 3 steps. Now, we're gonna talk about these 3 steps, and then I'm gonna come. Well, let me just talk about these 3 steps. I'm gonna come back to it. So, step 1 is the Fe3 from sand minerals is reduced to Fe2. Yeah, I mean, okay. I would just say I don't know if it has to come from sand minerals. It can come from Fe3 can come from any source, right? It doesn't necessarily, as long as it's there and it's not like it's like not in goethite or some mineral form where it's like solid form. But reduced iron. So that's step 1. Reduced iron from sand minerals and fertilizers is translocated down. So in other words, the iron has to be there. The iron has to translocate down, and then it has to be reduced. When it's exposed to oxygen, when water is retained above the gravel layer, causing Fe2 to oxidize to Fe3, forming a cemented precipitate layer. In other words, you got a lot of stuff going on in here in terms of it's a soil chemist's dream, really. I mean, if you're interested in iron, Fe3 is going. Well, it could be even organic iron, but it's forming into Fe3. Then it's reducing back down to Fe2. Then it's moving down the profile. It's encountering oxygen and going back into Fe3. Precipitating out. There's a lot of stuff going on. Okay.
Yes, absolutely.
This paper's awesome. I mean, it's crazy that there's just a tremendous amount of stuff going on. Now, I want to make sure we're clear. It says in some cases the high levels of iron fertilizer. The reason I highlighted that, Glenn, is that in this paper, this was one of the first sort of introductory discovery papers of the subject. And there needs to be a lot more work done, but I want to make sure that I'm correct when I say this, and one reason I wanted to have you on is so I don't want to be incorrect here. You all weren't able to actually identify the source of the iron, either coming from an inorganic or organic, source, right? So it could have came from iron sulfate from fertilizer. It could have came from the organic iron in the soil. It could have came from the iron coatings on the sands. I mean, you're not really sure exactly where it came from. Is that true?
Correct.
Was there any relation? Go ahead.
Irrigation water, it's not as likely as some of these other sources, but it's another, there are lots of inputs that could account for that iron. Yeah, the
iron in the water, I mean, it gets to depend on how much water, how much iron's in it, but you'd have to put on a bunch of iron from a bunch of water, and the iron would have to be through the roof to get that much on there, compared to the amount of iron that's going out on fertilizer. And you make a point of saying that in the paper as well. I just want to make sure that it's clear that we don't know. This is a question, not a statement.
Mm-hmm.
We don't know. do we know, or do we have any confidence in saying the iron is coming from fertilizers? You need to lower it. How confident?
No, we not confident.
Okay.
So the paper that has not been published yet, for my PhD, we added very high rates of iron to sand columns with different pH scenarios. And long story short, we added somewhere between 3.5 to 14 gears of iron applications, depending on what rates you would be using. And we didn't form these cemented layers in columns, right, in a greenhouse type of setting. So I think we addressed the pH part, but we didn't have the anaerobic conditions. And I think there's this whole piece that we're not looking at in this paper, and that I think is hard to look at, but we need to, is what contribution does the redox potential or the anaerobic soil conditions play? And that's I think that's the missing part here. And so
I mean, in theory, we shouldn't have an anaerobic situation in a putting green that's properly, has properly built. But I think it was even Dr. Gratz at UF published 15, 20 years ago. Even in aerated soils, there are clearly micro sites in that soil that are anaerobic. Just because you're at field capacity, quote unquote, it doesn't mean that you're not anaerobic, that you're completely aerobic. There's going to be some anaerobic zones in that soil. And in this case, what I'm getting at is, in this case, where you have essentially a perched water table above, this textural discontinuity between the gravel and the sand, you're going to have water moving down, and that lower boundary of that sand is going. There's no way it's going to have less water than the above soil. It's going to have more water because the water's moving through it. Yes. And I think, I think we need to make that clear, is that your putting greens have zones in them that are anaerobic. There's very little chance that you're going to completely eliminate all anaerobic conditions in a putting green. And you have to have that, really. I mean, you don't have to have it, but it greatly increases the risk of this forming, because that's necessary to reduce the FE3 to FE2 to get it to move down. Is that the case? Is that what
Exactly. Yep. That's the case. I want to, it's not in this paper, but if you ever are on your golf course and have a chance to dig a hole in a green and actually get the soil profile exposed, take a TDR probe and stick it in at different depths. We put some of that in a different paper, and right above the gravel, it'll be like, it's all relative, but the TDR probe might tell you 30% volumetric water content, and you go up a few inches into that sand, and it'll be like 2%. And the gravel is like 0, right? So
exactly.
You definitely have a band. That's
there's a gradient of water from the top down to the bottom, and it's very well engineered to do its job, and that is maintain a putting green and have some aeration and resist compaction. But there's this dynamic that exists for sure. So let's continue down through here, because I'm talking too much here. I gotta get moving here. But in some soils the pH was acidic, basically. In other soils it was neutral. In other soils it was basic or alkaline. And what you're basically in these paragraphs here that I have marked here, in these paragraphs, basically what you're saying is that in acidic soils it makes sense because it's moving. It makes sense that the iron's moving because it's acidic and it's more soluble and more likely to be reduced to Fe2. When it's not reduced, when it's not acidic and it's alkaline, there's a statement here where you're talking about the potential to be the iron to be reduced from the oxidation of sulfur. And I'm a little bit confused there, because in the cases where you're talking about, I'll just read it here. It says, excuse me, where is it at? We have present, okay. Some acidity may have been produced as a reaction product of iron sulfate oxidation at the sand gravel. In other words, the iron sulfate's oxidation process is reducing it down, I guess, it's where are you at? Sand gravel, which could result in mobilization of the iron from the root zone, above. Sulfur is a common component of inorganic fertilizers, and so the sulfate's been put in there from fertilizer. In other words, there's a source of sulfate. You're making that argument, and that's fine. The Hawaii low soil had a distinct sulfurous odor and so forth. I guess my thought process on that, when you're talking about the oxidation from using sulfur, I think there may be something there, but In other words, you're trying to explain the movement of iron in an alkaline soil. How could it move? And I think it could easily move simply by the oxidation of the organic material as well. So
I agree with that.
yeah. So iron is a great oxidizer of organic material, and when that happens, that Fe2 gets reduced down to Fe3 gets reduced down to Fe2. It's not quite as likely in anaerobic soils. It's less likely, but it can still occur, I suppose. Anyway, there's just some thoughts there. Now, these graphs. Do you want to go over any of these graphs? I want to get to the one that I like, but we can go over these graphs if you want to.
All I'll say is what do your eyes see with red color, and where you think those layers are when you look at the soils. That's what these figures essentially showed, and so
so we're looking at depth of the profile.
Correct. Yep. And then looking at the concentration of different elements, and so
So
the long story short is go ahead.
This Fe0 to Fed this is the ratio of the two forms of iron.
Yep.
Or
and
two.
The closer it is to one, the more likely it's a cemented layer, basically, like one that formed recently.
Okay.
If the ratio is really low, close to 0, like 0.1, it's not recently formed iron. It's probably iron from the sand. That's just inherent in the So as you see, like in the cemented layers, the ratio gets a little bit higher or closer to 1 because more of that iron is recently formed.
Okay.
So that's the idea.
That's a good explanation. Yeah, I wasn't clear on that. Good.
Yeah.
Thank you for that. Okay, good.
Yeah. And then I guess the next figure I think gets to what I could say on the figure above, but I think it's summarized the best in the one down there. Yeah.
This one here.
So.
Yeah, yep. I hadn't quite seen this sort of information displayed this way, and I think I don't want your readers of the article to skip past this thinking it's not important. It is important. Let's talk about it.
Yeah. So the figures that we were looking at before, like your eyes start to pick out relationships, right? Like can you actually scroll up? Scroll up once. So like you see like that bottom left graph there. Those lines kind of have the same shape, right? Like they were measuring all different things, but they all have the same shape. And so that tells me maybe those are related or correlated to each other. And so then that figure down below, it actually looks at the relationship between all this different stuff that we measure. And
so can you walk us through? So walk us through. So you have age, depth, soil organic carbon, pH, and then the forms of iron, and then you have manganese and aluminum on here as well. And it's what do you call it? There's a name for this type of
scatter plot.
It's a scatter plot.
Scatter plot matrix.
Matrix, scatter plot matrix, something like that. It's something along those lines.
So
if you're looking at this, walk us through. So if I'm looking at age and I'm going down this way, I'm going to come to the intersection where it's age and depth, right?
Yep.
Okay.
Yep.
So what does this mean when someone's reading this in terms of like seeing the dots on this scatter plot on the age depth panel?
Yeah, so it's just trying to correlate all the different data points, and so some of them wouldn't make sense to compare. Like, I'm trying to think. Like age and depth. Depth is just something we measured. Yeah. And so then, of course, like that wouldn't be related to age. But then you go down to a question we had was like, do we see more iron in older greens, right?
Yeah.
And this lets you actually look at whether or not that trend was there.
Okay. And by this here, the depth. Oh, you said age. I'm sorry. I was
picking one arbitrarily. So I mean, with age specifically, there wasn't a whole lot to pick out.
Okay.
But then you go to one like depth and soil organic carbon.
Okay.
So depth and SOC.
Here. Yeah.
So you draw. Yes. How do you read this? So you look at the connection between those two. So to the lower left of depth, and so that one right there where your cursor is, those are all the data points of the different depths and how much organic matter or organic carbon they had. And that one to me makes sense because the shallower the depth, the more organic matter you have, right? We see organic matter at the surface, and that's what this graph shows. Yeah, is that at the surface, the higher depths, which are more to the right, and then the organic carbon's higher.
So the depth unit for this variable here, the depth is up here, right? This is the depth, and this is 20 centimeters deep and 30 centimeters deep and so forth. To make sure everybody understands that. Okay.
Exactly. Yep.
And then I got something on my screen. And then the soluble organic carbon is over here on this axis over here on the right y-axis.
Yep. Basically in percent.
Okay, in percentage. Okay. So that's how you would read that.
It is. And then and then if you go like kitty corner, like to the upper right, that's like a mirror image of everything on the bottom left. And so that 0.75 number between depth and soil organic carbon.
Yeah, right.
That's the correlation coefficient, or the R squared.
So it's pretty good.
So it's or the R. Yeah. So it's like the closer that is to 1, the more perfect the correlation is. And so 0.75 is like, and that makes sense. We already know that the surface has more organic matter. So that makes sense, right?
Yeah, and any negative values, I mean, just the trend, the relationship is going the other way rather than up. And you see,
exactly. Yep.
Okay, good. Okay, I just want to make sure that we understand that this is an important figure and understand how to read it.
And I can call out some of the important. So a bunch of them were not important.
Okay.
You know, like age, for example, didn't really explain much here, but we only had 6 sites, and so maybe it wasn't the right data set for that. But you look at things like okay, so, some really key ones I think are, if you look at the FE, any of the iron ones, go FED. FED, and then and then go down from there. Look at aluminum, ALD, and FED. Yeah. It certainly looks like you've got, the more aluminum you have, the more iron you have. So there's a correlation between iron and aluminum. Yeah. And when we go back to the literature and look at, you mentioned the word sesquioxides. Oxides, those often contain iron, manganese, and aluminum. And in our data set here, we saw that iron, manganese, and aluminum seem to be moving together. And so, there's some validity to that.
Yeah, manganese and iron are, they sit right next to each other on the periodic table. Not that particularly matters in every case, but they tend to kind of have a similar dynamic, and a chemist would crucify me for saying that, but they have a very similar dynamic in their redox potentials and their solubility and so forth. In other words, manganese will oxidize, but it just won't do it quite as quickly as iron.
Yeah. Exactly.
Okay, good. Okay, so let's get to the very end here and wrap this whole thing up. And
sure.
And then I'd like to kind of frame it and put a nice little bow on it so people can walk away with something that's they can use if possible. So we just talked about all this stuff. The construction. Okay, we already talked about that. Good. Then I'm gonna skip the podology stuff because I think
that's fine.
That might put some people to sleep.
It might.
It wouldn't put me to sleep. I mean, I read it. I was highlighting it, but. We might lose some people on that. Okay, so let's go to the end here.
Yeah.
Okay. So I'll read the last little part here, and then we'll kind of have some bullet points. The iron-cemented layers described in this study always formed at the textural discontinuity. We've mentioned this phrase just so we understand the texture. What we're talking about is the texture of the above layer of the root zone is X, whatever that is, and the
soil texture. Yeah,
the soil texture is what it is, and then the texture of the lower gravel layer is very, very different. It's much more coarse, much more large particle sizes. And at that boundary layer creates a textural discontinuity. That's what we're talking about. There's a strong line there that we've intentionally created. That can also be created in nature. I mean, it happens all the time in nature, but we've done it on purpose to take advantage of what happens when you do that, and that is to hold the water up into the root zone for the turf grass to take advantage of. So that's what they're talking about when they say textural discontinuity. Formed a textural discontinuity or organic rich layers where drainage was impeded above a drier subsoil with a boundary of lower redox potential over higher redox potential. Therefore, we predict that iron cemented layers. By the way, I like this phrasing. By the way, I wish I did this more actually when I was writing. We predict. As scientists, we have to make predictions. And then we have to go test our predictions to see if they're valid or not. The model accounts for it or not. So I like that language. Well done. Therefore, we predict that iron cemented layers are more likely to form in soils with sharp boundaries in particle size pH, or total organic carbon, creating conditions of lower redox potentials of higher root zone redox potential. So what you've done is you've gone from golf in that sentence. You've gone from golf putting greens to this could really occur, but this is what we would expect to be necessary in order to increase the risk of it occurring. We need a textural discontinuity. We need iron. And we need some redox potential. We need the redox to be low, I guess. I mean, the iron needs to be in Fe2 in order for that to happen. Right. It generally needs to be anaerobic.
Yeah.
Okay. Okay. Well done on that. And then it says future studies should investigate the contribution of iron from irrigation and fertilizer. That's what I was saying earlier. We don't really know exactly where it's coming from. It's certainly, if you're applying iron, and this goes for lawn care operators or sport turf managers, even if you don't have a putting green, if you're applying iron, we all know about the phytotoxic potential of applying iron to the turf grass, but below ground, it can also occur, and the iron can actually cause issues. But having said that, I'm not so much worried about someone putting out a pound of iron per acre, spraying it out, 3 or 4 times a year. What I'm concerned about, Glenn, and the audience, is putting out granular iron as iron sulfate when we know, or we're very convinced, that iron is going to oxidize very quickly and not provide any agronomic value to the plant. There's very, very little evidence you're going to provide any agronomic benefit to the plant. But although I would say the risk is low, you're increasing the risk of something like this occurring without receiving any benefit from the application to begin with.
I agree with that.
Yeah. So I want to make sure that people, I've been hitting this hard, Glenn, is where with iron is that granular iron to me is not of any really agronomic value, meaning it's not going to increase the plant quality or the plant color. It's going to oxidize very quickly. And if you're loading it up and keep applying it, it's very unlikely that you have the exact conditions that's going to create a textural discontinuity and all these other things. But if you're looking to minimize your risk, you have to have 3 things: iron, you have to have redox, the potential has to be low, and you have to have a textural discontinuity. Well, you can control the iron. There's not a whole lot you can do about the anaerobic conditions per se when you're dealing with 10 inches down or 12 inches. Not a whole lot you can do.
Right.
And there's not a whole lot you can do about textural discontinuity.
Right.
But you can control the iron, especially when you're applying sources that don't have much agronomic value. Just eliminate them.
Right.
Right?
Agreed.
I mean, that's what I'm thinking. Even though we don't have strong evidence to say that this layer formed from iron fertilizer. We don't have that yet.
No.
But,
it is iron, though, and it's certainly what it could contribute, right?
Exactly. It could contribute. And I'm like, well, we don't need it to begin with. So let's just eliminate it. I'm sorry. I get all bent out of shape here sometimes. So
that's helpful. Yeah.
Okay. The conclusions: the layers from a textural discontinuity where redox potential is low is in saturated soils and high in drier subsoils. A layer must become cemented, or a layer may become cemented in less than 10 years, 1.5 millimeters a year. So you just took over a golf course and you were new superintendent there. You're maybe the second and third superintendent at this golf course, and it's 15, 20 years old. We oftentimes think of putting greens, about that age, considering redoing them. But even 10 years, potentially even younger than that, it's possible with the right conditions that you may have an iron cemented layer at that boundary layer and not know it. Because how many times do you dig up your green and look at the boundary layer? I mean,
not that often.
That often.
Yeah.
I suspect this is probably more common than people realize because they're not going out and digging down 12 inches and looking at that layer.
Yeah.
That's just my take on it. These management factors. I'm sorry, go ahead.
No, I wrap it up, and then I have some kind of overarching comments about testing and sampling. And stuff like that.
These management factors are common among sites across the world, leading us to hypothesize that iron cemented layers could form in any golf course soil with an abundant supply of iron and a redox potential boundary. And so that's the key. I mean, you need to have the source. It's kind of like the disease triangle, really. You need to have the source. You need to have the right conditions, and that it being the redox potential has to be low. And then you have to have this boundary layer that provides oxygen below it. There's an opportunity for oxygen to interact with the reduced iron from the above layer. So if we can if we can minimize one of those three, like the disease triangle, and if we can control this or control that, then the chances of it coming and creating a problem would be reduced, is what I'm reading from that.
In theory. Yep. That was our theory.
Okay.
So
what else you got?
Yeah. So I'm just thinking, take a step back, and because when people see this or they see these pictures, like everybody wants to be able to just grab a jug of some product and like get rid of it. Right. Or it's like, you'd love if there was just some easy thing like, oh, just don't use iron fertilizer, or don't, it's not, unfortunately, I think we're just not there yet. And I liken this to a little bit like the journey we've gone through with organic matter accumulation. Like, when did that research start? It's decades and decades and decades ago. But at the very beginning, I bet we were just noticing that organic matter is accumulating, and then they probably were like, well, this happens in grass prairies as well. And like, there's like a whole framework that's exactly the same as what we're going through here, except we're just like at the very beginning of it with this problem. And it's tricky because it's 12 inches down versus at the surface. But I mean, think of how much research every single year is going on with how to manage organic matter accumulation, and the debates about top dressing versus coring. And it's like, well, we still don't, I mean, there's a lot that we know, but it's like, there are still lots of contentious debates and different approaches. And like, that's how many, 80 years in, or I don't remember when that research started, but we're far further down the road that we observe the problem and then started testing how to solve it. We're still in the observe the problem phase with this problem, with the iron cemented layers. And so, yeah, when I went to UW-Madison and showed everybody these pictures, I thought they were going to say like, oh yeah, just apply this acid or something like that. Right. And I've worked with courses who've tried that. I worked with a course that they'd use the drill and fill machine.
Okay.
And they closed the course for 2 whole weeks. Drill and filled every single green, and they hand sprayed with a single nozzle. They sprayed an acid down every hole until it backed up and like bubbled up out of the hole. Really? Like, they had the whole entire crew do this. I don't know. It was a huge investment. And they thought that they saw some temporary relief that let them get through a tournament, but they were still renovating the greens 3 years later. So it's like, it didn't ultimately solve the problem. And then when I was there, I noticed that you still had the iron cemented layer at the sand gravel interface going horizontally. And then we also had iron accumulations, or maybe cemented layers, now going vertically up the sides of those channels.
Oh, really?
Yes.
Oh my gosh.
So now you have like a 3-dimensional, it's so
you have a tube,
anything like that, you have a tube. Yeah. And so it just, to me, highlighted like, okay, we are in the observation phase. You can try stuff, but we don't even have the right testing framework to be able to go back and say, have I made progress? Have I reduced the layer? Like, it's so hard to even measure the infiltration rate with a ring infiltrometer. Like, that's not really adequate to measure what's happening 12 inches down. So it's like we don't have the right toolkit still. And I think the best thing I think a superintendent could do right now is to get your hands on observing, and I mean, literally get a PVC pipe and go out to the areas that are struggling and pound that thing down with a rubber mallet and pull it out and cut it open with a Dremel tool or an oscillating saw, and look at your soil. How often do we actually do that? Look at the putting green soil profile. Yeah. And you can send those samples to a lab and get more analysis, but like, your eyes are going to tell you so much. And so, at least once every year or 2 or 3, I would be documenting, taking pictures, and then looking at changes over time. Yeah. And their labs do offer the right tests like that we did in this paper. It's not super mainstream. You might have to have it work with a consultant or, ask for them custom. I'd love to see our industry get to the point where our undisturbed soil analysis, right now there's so much focus on physical properties and on the sand size and bridging factors, and that's all super important, but that's all very engineer course construction, how things are on day 0. And then it's pretty unfair, I think, as superintendents, we're asked to take something that was designed to last, on day 0, and then it immediately starts changing. Organic matter is accumulating. There's no framework or way to understand all these complex chemical reactions that are happening.
Yeah.
I don't even know how to talk about the biological things that are happening. It's almost like even through all of undergrad and grad school, it was just like, oh yeah, that's really complicated. It's the black box. But it could be very important to understand how nutrients are cycling and moving. And so I just think we're still in the observation phase. Take soil samples, look at them for yourself, and as an industry, we need to get this way further along in terms of the amount of data we have and the amount of sites that we've looked at, and move from a physical properties only to a more nuanced approach, looking at the physical and chemical properties. So looking at the pH, looking at the amount of organic matter, not just at the surface, but lower down in the profile. And so
that's interesting, because I often get, maybe it's just because it's my world of soil testing, but I get inundated with that component, that part of turf grass management. I don't really have a lot of people calling about physical stuff, and I often tell people, if it were me, in fact, I just did it last week at the GIS, is that if it were me, I'd put down the soil sample probe and I'd pick up a soil profiler first.
Yeah,
It only goes 7 inches down, but I mean, it's not going to go all the way down to the gravel layer. But I think the soil profiler, which I'll have to show a photo of it if you're not familiar with it, I think that's going to give me, in many cases, more valuable information than a soil test will. And in your case, you're saying go one step further, just hammer down a pipe down into the ground, all the way down to the gravel layer, bring it up, split it in half, and take a look at it. And I'm like, yeah, I agree.
Yeah.
I mean, the information, and I know people say, oh, that's a lot of work, or I don't want to put a hole in my green, or it's going to take, the information you'll gain from that is far more valuable than I think you can imagine, especially, and to your question, Glenn, you said, how many people do that? I've never driven a pipe all the way down to the gravel layer, ever.
It's awesome.
Yeah,
you should try it.
Yeah, I know. I mean, what I'm saying, I mean, I'm sort of in that world, and I've never done it. So, I mean, for superintendents to do that, maybe not on every green, but if you have a green that your indicator spots in your putting greens, which ones tend to be poor and which ones show up first. Well, I mean, you can at least take that opportunity to go down to the gravel layer, pull it up, and rule it out. If it's not that, then you're good. Okay, it's clear all the way down to the gravel, and through the gravel, you're good, and the drain pipes, whatever the case is, you're good. And if you're not in UHA spec, if you're just have sand on top of native soil, there's still a discontinuity there, textural discontinuity at those layers as well. So I don't know if you diagnosed the iron cemented layer in that case, but it would seem that it would be possible.
It is possible. Yep.
Yeah.
Yep. We've seen that before.
Yep. Oh, you have? Okay. Yeah. So
I don't know if it was causing a problem. That's the only thing, but I've seen iron accumulation in that scenario you described as well.
Okay. So, yeah. Well, I would just encourage people to, I mean, I don't want to say put down the soil testing probe, but at least pick up a soil profiler. I think, you know what, Glenn, now that I say that, I think they might have a soil profiler that's 12 inches long, or maybe even longer. I think I've seen one where I have one downstairs, but it's only 7 inches, but I think they might have a longer one. And then, then it pulls open. If I'm not mistaken, I think that might be from that company that, I can't remember the name of the company, but they may have a 12-inch one or a 16-inch one or something. I don't know. But
that's a good question. Yeah. One tricky thing too is a lot of the times the depth is not 12 inches.
It's more than 12 inches.
It's more than 12 inches.
Yeah.
So if I'm doing it, I haven't used one of those profilers for this depth, but I'll take like a 2 foot long, 2-inch diameter PVC pipe, cut it off at 2 feet. I'll throw it on the grinding wheel and sharpen the bottom.
Yeah.
Go on the drill press and drill a hole through the top. Get a big screwdriver as a handle, and then go out to the green with a rubber mallet and just wail on it.
Hammer that sucker down,
And when you hit the gravel, keep going and go all the way through the gravel into the subgrade.
Oh,
pull out the whole plug, and then you'll be able to actually see.
Oh, really? You can. Okay. Well, I wouldn't. I didn't think about going through the gravel, but if you can get it to go through there, sure. Yeah.
If you can get it to, it's hard, but you.
Yeah. Well, that would definitely eliminate any variation. I mean, you would definitely have if there is something there, you would see it there. Right. That's basically what you did in this study? You went all the way through the
Mhm.
gravel layer, and then you split it in half, and you opened it up. Okay, wow.
Yeah. Mhm.
Oh, well done. Well, Glenn, is there anything else before we go?
No, just keep digging. That's my advice. And I hope that as an industry we get further on this. I'd love to see the same amount of sampling and data that we have for like plant nutrient analysis and interpretation, where we know like this amount of iron is. We have words like high, medium, and low, which are kind of fraught, but I'd love to be in a place where we have enough data to say stuff like that. In this case, like, well, if you're whatever measurement toolkit we have, that's where we need to get to. But it starts with digging a hole and putting a pipe in the ground. So start there, and we can all get there together.
Awesome. Well, you and me both. I wish we had more data on soil sampling and testing and tissue testing and all that stuff. I think the analogy I use is maybe 100 years ago we were blind completely. Now I think our eyes are open, but our glasses are off. I mean, everything's kind of blurry. We can kind of see some things here and there in soil testing. We can kind of see the general direction we need to go, but it's really blurry. And I think if we keep progressing, keep moving forward, if we can get enough funding. The problem is we don't get enough funding for this work. No one wants to fund soil testing work. I don't know why. But we can eventually get to where we're wearing glasses, and then we have more confidence. I think that's our progress. So we've gone from blind to walking with no glasses on, and we're kind of we kind of can see the truck in front of us about to hit us. We can kind of see the over there. There's someone walking, but we don't really know who it is or where they are. That's where we are now. So okay, all right, everybody. So on Monday, thank you, Dr. Obear. Appreciate it. Hang on, real quick. Don't hang up. I hope I'll be back on Monday. I'm scheduled to be back on regular routine next week. And then I'll fill you in on everything that's been going on. And we're going to start back with nitrogen. So not back, we're going to start with nitrogen next week. I have 5 or 10 more papers of iron, but it's too late. I got to get on to the next subject. And we'll be going over nitrogen. And on Wednesday night next week, we'll either do the next pH paper or we'll do the nitrogen cost paper, which is probably what everybody really wants to see. So look forward to that next week. Until then, guys, I really appreciate Dr. Obear. Hang on real tight, and everybody for showing up today. Appreciate it. We'll see you Monday morning. Bye.